Hey everyone, thanks for tuning in. Wanted to do a brief video on statistics. It's something that just comes up in just about every conversation about testing because you not only have to have a good testing methodology and control for a lot of variables to really isolate things, but you also have to be savvy with the statistics to be able to know when and what to apply in terms of statistical testing. So this one is basically building off the previous video that I did on my YouTube about statistics, because that video showed it probably, I would say, extreme basics. The kind of stuff that I think you'd see in like Brian Litz's books, where he just tries to explain the basics of a distribution of metrics, scores, group sizes, velocity measures, that kind of thing, and showing you kind of what standard deviation is, what extreme spread is. That's all like extremely basic stuff. And that was in my first video. This video is a little more advanced, so feel free to skip out on this if you did not watch the first video, or watch the first video before you delve into this, because that first video sets the foundation for this. Statistics is a massive field. I've been in education and training in it for 10 years. I've been applying it now for 25 years. It is not something that you can just pick up one book and then all of a sudden, know everything, or read Litz's, rudimentary explanation about stuff and then easily pick up on it and know it. It takes some depth, it's one of those things, I draw the analogy, I don't tell Jim Borden how to build an action. I know that requires lots of depth of training, understanding. It would take a long apprenticeship of me hanging around the shop to really figure all the stuff out. And same thing with statistics. So I respect, people's training and what they put into it. And it's, and so anyway, and I'm happy to, I think I put this on Patreon. Jim Borden is going to be working with me on doing fire control testing. So I am going to be delving into it with him, which I super appreciate, because that's an area where I know I don't, have any depth, and I certainly don't make any assumptions when it comes to that. So, I told Jim, this is really great for me because, I'm almost a blank slate here, willing to learn and looking forward to learning what I can. But anyway, it's kind of the same thing with stats. So I just respect people's expertise. And anyway, so there's a few different things to go over. And again, this is super brief, super rudimentary, but it'll just give you a little bit of more understanding that hopefully will inform you a little bit more about statistics. But the first thing is probability value. So anytime you run a statistical test, for certain statistical tests, the ones that we're going to run, ones that I usually run here for the types of tests that I do, will give you a probability value. There are other tests that don't give you a probability value. Those are like super, way more sophisticated tests than we're looking at here. I've used those types of tests in scientific research papers and whatnot, and they don't give a probability value. They give what's called the goodness of fit and other things, because they're looking at statistical modeling. That's different than this. This is pretty simple. This is probably the simplest level of statistics that you could do. And to the extent that I can use the simplest, I will. There's some data that I have, though, where I probably will have to use the modeling approach, which, and this is after years of collecting data, so I can collect a good model. And I'm going to do that on some atmospheric data that I've been collecting, but that's way down the road. But for now, the stuff I do, I try to keep it simple, just so we can easily understand, okay, this is different from that, and just keeping it simple. And so most of the tests that I run for these tests are going to give you a p-value. That p-value is basically probability that there is a real difference in your data, that it's not due to a chance phenomenon, okay? And so here's the interesting thing about probability. It depends on your sample size, and it depends on how large the mean differences are, and then how small the standard deviations are. Okay, again, like I said, if you want to know about your distribution, standard deviation, ES, what all that means, go check out my first video. I'm just doing this one, kind of building on that one. So I'm not going to explain what all that means. But basically, for example, you see this distribution here is the same exact size, let's say, of this distribution. But if this is a much larger sample, you may get a probability value of 0.05 or less, which is the industry standard for the cutoff of like what is statistically significant, which means it's not due to chance, or it's not statistically significant and it's probably due to chance. But in a small sample, even with the exact same scores, exact same shapes of the distribution, exact same mean differences, a small sample can give you a probability of 0.5, which means that it's due to chance. Okay, so p-value is heavily influenced by your sample size. Okay, and so and it's also influenced by how far your distributions are and your standard deviations, but sample size is a very important thing for p-value so that you could you have to adjust your methodology for how many shots you take to be able to say, okay, is this a sample size that's adequate enough to be able to run my statistical test? Now, there's two other factors that interact with all three of these factors interact, and I'll go over all of them. But so p-value alone is usually not the best thing to just look at right away. You have to also look at your power analysis. So power analysis is the probability of finding an effect. Okay, and so if there is a difference between two conditions, two experimental conditions, let's say in this condition you have, I don't know, annealed and not annealed, okay? And let's say that's the same thing here, and we'll just use that example here for the whole thing. Annealed, not annealed. Let's say you have a large sample. You collected tons of data of annealed brass, tons of data of not annealed brass, and let's say you shot a ton of 5-shot groups. You got a distribution like this, large sample size. That's going to give you adequate power to be able to detect that there is a difference, to be able to even get you to where your p-value would be 0.05 or below. If you had a small sample, then you have inadequate power, okay? You may not have the power to be able to detect a difference, and you'll get a p-value that is much larger than 0.05, okay? And so now that's not the only thing going on here. The third thing is called effect size. That's the magnitude of the differences between your means. That is also important. So if you look at your distribution of scores and they're really close together, the means don't have a whole lot of difference between them and the standard deviations are about the same, you're going to have what's called a small effect size. So it's basically the magnitude of the difference between whatever distributions that you're assessing. And then let's say you have this, means are farther apart, SDs are the same, and well, now you have a medium effect size. Your effect is growing. Your annealed distribution is much farther now than your non-annealed distribution of scores. Now let's say your distributions overlap just a very little, a tiny amount. That means you have a large effect size. And that's where, okay, wow, we're seeing a large effect between, the annealed condition and the not annealed condition, okay? And effect size is influenced by, guess what? By your distributional properties. So how far apart are those means, and how are those standard deviations? Are they tight or are they really big? So basically, how much those distributions fall apart from each other in terms of average, and then how much do they overlap, okay? And that you can have a large effect size, but a really, really small sample and still get a probability value of above 0.05. So really what you're trying to do is you're trying to give yourself enough power to detect a statistical difference. If you know what your power is, if you know what the effect generally should be, you can actually estimate what sample size you need in order to have a test where you have enough in your sample to detect a difference. And then if you know the general effect size, that helps you estimate your power, okay? So this is where it becomes difficult in the shooting sports, because when people ask me, well, did you have enough, or you didn't get a statistically significant difference, or you did, but your sample size doesn't look that big. And I tell them, well, first of all, I had no previous data to help me determine what the potential effect size was for this type of phenomenon that I'm testing. There's really nobody, well, I guess, except for Brian Litz, and maybe there's a few others that I've had contact with that have shown me some really good data and whatnot. But like for the most part, we don't have a sort of wealth of information for me to be able to sort of determine an effect size. So I don't know what the effect is going to be, I guess to say, going into any test. So that's why I don't a priori, kind of figure out, okay, this is the amount of groups I have to shoot for this test. I don't do that because I really don't know what the effects are going to be. What I do is I just start shooting the test, and then I just start measuring group size and other characteristics, velocity, whatever it is I'm looking at, precision or ballistics or both. And I start just eyeballing it from there, essentially thinking, okay, well, I'm sort of determining what the effect size is after a handful of shooting several 5-shot groups for each condition, and from there I'm making estimates basically in my head. I've done these statistics. These are probably the simplest, most rudimentary for, I don't know, 30 years or so. So I kind of just looking at it will know right away, okay, I think the effect size is going to be this or that. And then I know, okay, based on that, I wonder how many more 5-shot groups do I need to shoot to be able to have the power to detect a difference, okay? And so essentially, I would love to have previous studies to help me judge what the potential effect size is. I do now with my own studies, but I don't with really others. But that's an important metric to look at. The effect size metric in and of itself, once you do a test, is very important, because you may find something with like a really small effect size, and it may be something that may be difficult for you. Like maybe you find that deburring the flash hole has a small effect size on ballistics. Okay, maybe. And maybe you think, well, I don't have the $100 to buy a tool. I don't have the time to do that with 300 pieces of brass. I don't need that level of precision. I don't care. And so in that case, this small effect for that particular operation is not meaningful to you. And that's fine. I mean, you pick what you need to do. You pick what you can do. And, if it's meaningful to you, then that's fine. Generally, large effects are meaningful to kind of everyone usually, but even so, you may not find meaning in some things that have a large effect. But once you get down to like the medium and small range, that's where sort of decision-making processes come into play. Is it important for me? Is it meaningful? It also highlights like sociological studies where they have huge sample sizes. So they'll study an entire social phenomenon, have 20, 30,000, 40,000 people in one experiment, or not experimental condition, in one research condition, and then maybe 20, 30,000 in another. And so they have more than adequate sample size to detect whether there's a difference in those populations. But the effect size is tiny, and it's generally like super duper small. So you get these samples where they're massive, and the probability value is less than 0.05, usually way less than 0.05, because their sample's so big. They had way more than adequate power to detect a difference, but the effect size is tiny. The general distributions between the two, the mean averages and the standard they're just not that much different. The mean average is not that much different, even though the standard deviations may be the same. So in that sense, you can say, oh yeah, that's a statistically significant sociological finding, but it's like pretty near meaningless because the effect size is tiny. Okay, so anyway, so that kind of decision stuff needs to happen, with you also. Do I really pay attention to things with certain effect sizes? For me, for testing, generally what that means is, if it's a small effect, that impacts my power. And so my power, if it's a small effect, I'm going to need a larger sample size to then have the power to detect that small difference. Okay, so that's how all three of these interface in various ways. So simply, running a statistical test and finding a p-value, yeah, that's important, but you also have to make sure there's considerations for your power analysis and your effect size. And these are the things that I do behind the scenes, and I'm literally kind of doing it on the spot as I'm analyzing data from tests and going, okay, this one is looking like a small effect. I'm going to have to shoot more if I'm going to be able to detect it. Or, wow, look, this effect is becoming large. Like, I really don't need to come out for another, one or two shooting episodes to really shoot, dozens of more 5-shot groups to figure out that this is already a large effect and I probably already have an adequate sample size. I probably don't say those things in the videos, as I demonstrate the p-values, but certainly these are the things going on in the background as I'm looking at data and understanding, what all of this means. Again, this is all why I say, I don't tell Jim Borden how to build an action. I believe he has all of that requisite understanding and background. I don't have to, question that. I just know it's there. So anyway, so that's all going on at the same time. Quick, and there's more, by the way. These are just the sort of additional things that I think Brian Litz should have taught in a lot of his rudimentary beginner stat stuff, because these two things, how they interface with p-value and the importance of basically all of it, is critical in understanding and just having a basic level of interpretation of what's going on with that data. Okay, and then just some quick other things about stats. There's tons of different types of stats. There's tons of different ways to do power analysis. There's tons of different effect size metrics. Again, I don't tell Jim how to build an action. Based on my depth and my understanding of all of those different metrics, I know which ones to select. I know which ones apply to certain situations. And so, but there's tons of them to choose from. In terms of the statistical tests themselves, for like just testing whether one, sample is not due to chance, different than the other. T-test is the name of the test where you're testing only two conditions, like let's say annealed, not annealed, okay? And in an ANOVA or an F-test, ANOVA is the same thing as an F-test. That's where you're testing 3 or more conditions. So let's say you're testing, primer seeding depth of flush, primer seeding depth of 0.003, primer seeding depth of 0.006, primer seeding depth of 0.009, primer seeding depth of 0.012. You may, I don't know, maybe another condition there, but there's definitely more than 2. That's where you run an F-test or an ANOVA. And from there, it'll give you a p-value. And if the p-value is equal to or below 0.05, again, the industry standard, then what you have to do, that only tells you that there is at least one difference between your distributions here. That doesn't tell you that they're all different, okay? So what you have to do so there's at least one difference, but that doesn't really tell you. I mean, you can look at the data and go, well, maybe the difference here, maybe the difference is here, maybe the data is large effect sizes and you can kind of glean from it. Yeah, this is probably different than that. That's probably different. But to know for sure, you have to run what's called a post hoc test. Okay, and that tells you where those differences reside within the condition. Okay, so the F-test or the ANOVA will tell you, yeah, there's at least one difference between these distributions, but then the post hoc test can tell you like where they're different. Okay, these two are different, and then this one's different than that one, and then that one's different than that one. Okay, and then based on that, you look at it and go, okay, so here's where all the differences reside, and then you make your interpretation from there. Based on all of these differences, it looks like, seeding your primer at 0.009 with that cup depth and that particular primer with the height of that cup and the typical anvil protrusion, it looks like this is where it's the smallest set of groups, where you have the most precision based on all the differences that you're seeing there. Okay, so that's called a post hoc test. And again, there's multiple post hoc tests to choose from. And so again, having that depth of statistical training tells you which one can I use under this particular situation, because there's several of them that you can use. Okay. Anyway, so yeah, those are kind of the simplest testing distributional differences. I'm not going to go into correlations. I think I went into correlations and regression coefficients and multiple regressions in that longer video that I put on YouTube. So I'll just refrain from that. But let me just do one other item, because it is important, because there's a lot of people out there that think that, none of these tests were done on a railgun, so they're all useless. And I get that. I get why people think that. They think that the railgun, just obliterates all potential variables and they're easy to use. And well, no, that's not the case. I mean, a railgun has many opportunities for error, sometimes more so than a bad gun. I've actually been in railgun matches where I've driven home, grabbed my bag gun, and thought, I'm going to just use my bag gun for this rail match, because this rail is I'm having a lot of problems with it. But in general, if everything is set up correctly, your rail is working great, then yes, the rail does give you very consistent, repeatable aim point from shot to shot. But what I do with my test with my bag gun is I actually I cherry pick the conditions. I only go out when there's no wind at all. The atmosphere is perfect. I'm usually the only person on the range, so there's nothing distracting me from shooting. I can take my time shooting a 5-shot group. And so essentially, I got no problem getting repeated aim point out of a bag gun, none at all. And so what I find is using the bag gun is just fine. There's no actual need to use a rail. The two things I've also found with the rail: one, I've had some problematic sort of fire control issues with one of my actions, but once I put a 1.45 diameter unlimited barrel into a barrel block, clamped it down, and turned that action on it, and that was a Hummer barrel, it's just started shooting great no matter what. So there's what's called a masking effect that may occur with a type of setup that you see with a railgun, where they tend to run these super thick, rigid barrels, and they're clamped in by these barrel blocks. So so my conclusion to that was, we got to be careful of masking. They may actually mask an effect when it's there. The second thing, it has to do with the actual statistics. So what happens if you've ever shot a railgun is, they tend to shoot tighter groups. And so you tend to get much smaller groups in general with a railgun. Again, if it's set up correctly, if conditions are great, they will in general shoot a little bit smaller than a bag gun. Okay. But that doesn't matter. We don't care about the actual magnitude of the groups itself. We care about whether a certain experimental condition can change that magnitude. Okay, so with a railgun, you get what's called small within group variability. All right, and so what that means is your distributions are very tight. So you have very little distributional standard deviations. They're generally tight. With a bag gun, they may be a little bit broader. They may show the same pattern as a normal distribution, whereas this distribution is called a platykurtic, and it actually, statistically speaking, has more problems when you run analyses on it than this one. The only way to take a platykurtic distribution and try to get it to kind of show the form of a normal distribution is to shoot way more shots, so a larger sample. All right, so basically that's the only way you can get a platykurtic to start trying to take the shape of a normal, is you have to shoot tons more shots. Now, in an unlimited, how much is an unlimited barrel? 1.45 straight barrel is $500-600 chamber job. it has, it's not going to last forever. So you're talking about I might burn out an unlimited barrel trying to get my statistics to be able to be good enough to run a data analysis on them. Whereas with a bag gun, I pretty much get this distribution right away. And so I don't have to shoot a larger sample to then eliminate the small within group variability and increase it to where you see in like a normal distribution. So statistically speaking, it's a real bad idea to use a railgun. Second, most people use bag guns. Railguns are extremely rare, and so why would I run a test using a railgun when the effects may only generalize to the railgun platform? I want to use a bag gun so that the results generalize to what people typically use, which is a bag gun, right? And finally, the other thing that I found is when I've shot with a bag gun and I found effects, like the primer seating depth is a clear and easy one. I found the effects in a bag gun where there's an ideal level of seating depth for that anvil to be compressed at, and I think it was 0.008, 0.009, something in that range, right? And it was statistically speaking smaller than all the other ones. Then really crushing your primer cup way deep with like 0.014 or something based on the cup depth and the primer that I was using. If I seated that far in, it was literally starting to kind of crimp down on the cup and kind of maybe damaging the anvil somehow. I don't know. And then let's say flush, okay, which is basically it's just seated enough to be flush with the case head, okay? So we'll call that zero seating depth. So that I did a bag gun, got really good normal distributions for all of my distributions. I ran the statistical tests. I had adequate power. The effect size was pretty large. Everything looked really good statistical wise, and it was very clear that this was best. So I thought, well, let's see if the railgun may mask this effect. So when I was going out to I don't even know. Oh, I was testing Craig Kensler's new rail design, the rail design that I'd worked with Craig on. And so I thought, well, while I'm testing this rail, I might as well just do a quick check to see, will it mask? And so I loaded, I think it was 15 rounds or 10 rounds, I forgot, of each of these, And so I thought I'm going to shoot two or three 5-shot groups of each. So, 3 5-shot groups with 0, and then 3 5-shot at 0.008 seating, and then 3 5-shot at 0.014. And what I found was exactly what I found with the bag gun, is that the groups were large. The groups here were very small, and then the groups here were very large. And so just doing a quick check, again, not a full test, but a quick check, I found, okay, the railgun is not going to mask. Is probably not likely going to mask the effect that I found with that bag gun. So essentially, I got verification that this is an effect that's going to generalize, from a bag gun and with a rail gun. And so I call that a generalizable effect. And so anyway, those are just some. Again, just some basic statistics on things and reasons why, you may see some tests and think, oh, well, there wasn't really a big sample here, or gee, he didn't shoot with a rail. Well, there you go. This is why, and helps explain it. Now, again, there's way more to it than this, but I just want to give an overview of another set of basics, because I think that at least knowing this gives a little bit more context. Not all of it, but a little bit. Again, I don't tell Jim Borden how to build actions. I respect that expertise. However, sounds like I'll be learning some of that expertise here real soon, and then I think I can go into more depth and get more understanding, from that whole fire control process. But anyway, just trying to give you a little bit more here with the stats. All right, everyone, we'll see you.